Welcome to Game Theory. This is section 32 on behavioral strategies. So in normal form in the last section, we talked about using mixed strategies techniques, where if we had a matrix, we could weight each of the pure strategies by a particular proportion to figure out what the expected payoff was with mixed strategies. If we have extensive form, we can use behavioral strategies. So suppose we have a game tree as shown here. This is figure 32.1 in your text. So we have two players, A and B, Anne and Beth, and they each have some strategies. So A and B have three different turns, essentially. A has turn 1, where A can choose to play A1 or A2. In the turn here, in the second information set A has, A can play A3 or A4. And in the third information set, A can play A5 or A6. B also has three information sets. B can play B1 or B2. B can play B3 or B4, in this small information set here, or B can play B5 and B6. So let's just focus on this first player, player Anne. We want to build behavioral strategies by looking at one element from each information set for the player. And we want to start to see how can we use information about how a player would choose if they only were in that information set, which direction they would choose, and use that to build up an overall long-term strategy. So that way, if they ended up in an information set, they knew exactly how they would play. So let's consider the different combinations that A could choose. In player A, if A was an A1, they could choose A1, A3, A5, or they could choose A1, A3, A6. If they chose A1 in the first information set, A3 in the second information set, or A5 or A6 in the third information set. A choose A1, A4, A5, A1, A4, or A6. Those are options. Choosing A1 in the first information set, A4 in the second information set, and A5 and A6 in the third information set. A could also choose A2, and then A3, A5, A2, A3, A6, could choose A2, A4, A5, and A2, A4, A6. These are the 8 possible combinations of A's moves, but some of these moves might not be necessary. We could reduce down the information set. For example, if A chooses A3 at any point in time, we know that A has no more turns. A never gets to A5 or A6. So, and if A chooses A2, A never gets a second turn. So we can reduce down the information set. We can say that in these particular 4 information sets, these reduce down because if A chooses A2, A never gets a second or a third turn. And here, if A chooses A3, A never gets that third turn. So we can reduce these down. But if A chooses A1 and A4, following down A1 and then either A4 in either of these branches, A gets a chance to choose A5 or A6. So we have reduced down our information set to 4 strategies: A1, A3 dot, A2 dot dot, and then A1, A4, A5, and A1, A4, A6. And these reduced strategies will make our life simpler in the end. And so the question is that if we know how A would play if it was a choice between A1 and A2 or A5 and A6, how would A choose to play if A was faced with the choice A1, A4, A5, given in those strategies? And that's our big idea here, is to use the probability of play inside each information set to determine the probability of a behavioral strategy. So suppose we know that A1 plays, or that player A chooses a move A1 7/9 of the time and A2 2/9 of the time. These are disjoint information sets, which means that the probability of playing in one information set does not affect the probability of move in another information set. So since the information sets are disjoint, that means that when we look at them, we can multiply their probabilities together. So that using these probabilities, the probability of play in A1, A2 dot is the same as the probability of play in A1 times the probability of play in A2 times the probability of play in dot, where here the probability of play in dot indicates that we have that it doesn't matter which choice we choose, so the probability is 1. So this is equal to 7/9 times 1/7, which gives us 1/9. So the probability, continuing on in this fashion, we have the probability of A1, A4, A5 is equal to 7/9 times 6/7 times 1, which equals 6/9, or 2/3. The probability of A1, A4, A6 is equal to 7/9 times 6/7 times 0, which equals 0, because A would never choose to play A6 in this particular game. And the probability of A2 dot dot is equal to 2/9 times 1 times 1, which equals 2/9. And so it's important to note that we have 1/9, 2/3, 0, and 2/9. And these are the 4 different options that A would choose to play. And if we looked at the sum of 1/9 plus 2/3, which is equivalent to 6/9, plus 0/9 plus 2/9, this sums to 1. And the probability of A's choices should all add up to 1. So this is valid. So what this allows us to do is to build the probabilities of the behavioral strategies using the information about how a player will choose in each information set. So we only need to know how the player chooses in each information set to build the larger probability. And we may also want to know how the behavioral strategies influence choices within a particular information set. So let's go back to the game. In the games that we're playing, we have perfect recall. So players know that everything that has happened in the game, including their own moves. So given a mixed strategy for A, we want to find the equivalent behavioral strategy for each information set. So we look at each information set and we take note of the specific positions available. So for example, if we're in this first information set here for Beth, we take note that we have B5 and B6 available to us. We know everything that has happened, including everything that I have moved. We can't predict future events, so we don't know necessarily that A will choose A6, but we know everything that has happened. So B knows if they're here, that A3 or A4 has happened, or that A1 has happened. We know all options are presented, and we exclude any strategy that doesn't match the information set history and options history. So we let, if AJ is in an information set, it's a choice in an information set, then the probability of an occurrence in that information set is the sum of the probabilities of all the strategies with AJ divided by all the possible histories with AJ. So for example, if we let the probability, now we know the probability of the behavioral strategies, and we want to find the probability of the moves within each information set. So for the probability of A1, move A1, this would be the probability of A1, A3 dot plus the probability of A1, A4, A5 plus the probability of A1, A4, A6, because A1 is present in each of those options. And the sum of all the options at this point, A1 is present in no option at this point is disregarded. So here, this is because at this particular point, no option is disregarded because A1 is at the beginning of the game. No option is disregarded here since A1 is at the first move, at the first node. So what we get is this is equal to 0 plus 0.3 plus 0.3 divided by 1 equals 0.6. The probability of A2 is equal to the probability of A2 dot dot, and that's the only case A2 is present, divided by 1 because A2 again is present in the first one, 0.4. And note that since A1 and A2 are in the same information set, the sum of those two probabilities has to equal 1 because they're the only two pieces in that information set. So that's a good check. The probability of A3, it's only present in A1, A3 dot, but to get to A3, we had to go through A1 first. And so this is 0 divided by the probability of A1, which is 0.6, which is what we found. So this is 0. And again, this is we divide by the probability of A1 because A1 is in the history of A3. We had to, when we looked back at how we got to A3, we had to go through A1 first. In the same fashion, the probability of A4 would be the probability of A1, A4, A5, plus the probability of A1, A4, A6, divided by the probability of A1 as its history, which is equal to 0.3 plus 0.3 divided by 0.6, which is equal to 1. Alternatively, we could have said that 1 minus 0 equals, so the total probability minus the probability of A3 equals the probability of A4. That would be another way of looking at this. Rather than doing all the calculations, sometimes you can use pieces of information that you know. So the probability of A5, we say, well, we know that this is a probability of A1, A4, A5, but we know we had to go through the probability of A1 and A4. So since we went through the probability of A1 and A4, this means we went 0.03 divided by 0.06 because the probability of A1 and A4, so let's do an aside calculation, the probability of A1 and A4 is equal to the probability of A1, A4, A5, all the different combinations where we have A1, A4 present. So A1, A4, A5 plus A1, A4, A6. So this is 1/2. And this probability of A6 is probability of A1, A4, A6 divided by the probability of A1 and A4. And again, this is equal to 1/2. So we've seen pairwise that these two values sum to 1. And so 1/2 plus 1/2 equals 1. So in this information set A5, A6, we equal 1. In the information set A3, A4, we equal 1. And the information set A1, A2, we equal 1. So within these information sets for this game, as demonstrated here, for player A, we equal 1. So if you have any questions, as always, please let me know.